Hey everyone, so today I wanted to talk about the Azure Sphere, the MT3620 that you can buy over at Seed Studio website for about $85, and how you can connect that to an Arduino over I2C. So I'm going to make a series of videos. Some of them will talk about the hardware configuration, like how to physically connect it. I'll talk more about I2C or I2C protocol, and kind of look at what's over the wire. We'll hook up a logic analyzer and that kind of stuff. But today I just want to talk about the software side of things and how we could program an Arduino so that the Sphere was able to talk to the Arduino, communicate to the Arduino, and get data sent back and forth. So on Seed Studio's website, you could get a pinout map that talks about, for each pin, the different protocols that are supported. There's like GPIO, there's analog, ADC, pulse width modulation, all this kind of stuff. But we're going to focus on I2C, which is the SDA and SCL lines. Sorry, I jumped one notch too fast. If you go over to GitHub and you search for Azure Sphere, we're going to look at these Azure Sphere samples. That's where we're going to spend our most of our time looking at that I2C sample there. But there was another one that comes up that I think is pretty useful. If you go into this repo and click on images, there's a bunch of images that are just focused on what you want to do. So if you're doing ADC or pulse width modulation, this is good. If you're doing GPIO, this is good. In our case, we're doing I2C, so you could click that, and you'll get a nice visual that's focused on, like, if you're using I2C3, this is the clock line and this is the data line. If you're using I2C2, this is the data line and this is the clock line. You can see that they're flipped and stuff. So this is like a really nice visual to be able to see that. But back over on GitHub, we search for Azure Sphere, and this first sample is the one. And so basically, what you're going to want to do is clone this onto your local machine. I can have a different video about how to set all this up, but basically you're going to clone it, and in the samples we're going to be focused on this I2C sample. So cool. So I've loaded that up, but here I can just go ahead and close the folder and open it again. So once you've cloned it, you'll have this Azure-Sphere-samples, and you're going to just go ahead and say open local folder, navigate to that, and go into the samples and the I2C sample, and open that as your local folder. And then we're going to look at main. And this sample talks I2C to a device, and it's basically built to talk to an accelerometer. I've got it hooked up to just talk to our Arduino right now, and Arduino doesn't have any code really running in it. So let's set a breakpoint down in main at the bottom here, and let's walk through this sample. So you're going to make sure that HL core is set up. And again, I can do another tutorial on kind of how do you use Visual Studio with the Azure Sphere. I'm assuming you've walked through all that already. So we're just going to launch this tutorial. This is an I2C tutorial. And again, it's connected to a Sphere, or it's connected to the Arduino, but the Arduino doesn't have any code running other than in loop every second. We just wait for a second and then we loop again. Cool. So let's go ahead and F10. So down here you can see I have an output shown. So I went to view and then the output window to show this output window. And then in the drop down, I chose device output. So you're going to want to do that so you can see kind of what's going on. So we're going to go ahead and F11, step into that init peripherals. The beginning here is stuff that doesn't have anything to do with I2C. So I'm just going to kind of gloss over that for now. We can look at that in another tutorial if you'd like. So now we're in the I2C or I2C, depending. They're both correct. So the I2C master open, and this we're opening. Let's peek the definition. we're opening on header 4, pin 6 and 12 is basically what this sample's using. So we're going to go ahead and open F10. We're going to set the bus speed. So you could set the bus speed faster if you want. This is standard speed, which I'd recommend if your wires are any kind of length for I2C. Slower is usually better. So I think it's still like 100 megahertz or something. It's still decent. Let's go ahead and we can peak definition that as well. Yeah, 100 kilohertz. Sorry, 100 megahertz. Wow. Yeah, so it's 100,000 times a second, which is plenty fast. And then here we're setting the timeout. So whenever we're trying to do a read on that data, we're waiting 100 milliseconds to see if that data is ready or not before we time out. I'll do another talk about the wiring, and we can look at the protocol with the logic analyzer. But let's go ahead and set that to 100 milliseconds. Good. And then this is the default target address. And so this is when we're using some of the libraries like the POSIX read and write calls. It'll use this default address that we've specified. And let's go ahead and peak definition that as well. And so that default address, this device is the address is 6A. And so that's where it's going to be talking to. And we'll be seeing that later, that 6A come into use. Cool. And so far we've had no issues. We were able to open that, set our bus speed, set our timeout of 100 milliseconds, set a default address. And now we're going to actually try to talk to the device. So read me. So let's F11 into that. So who am I? So it's going to do I2C master. It's going to write out this command of 0f saying, who am I? And then it's going to try to read back an answer to that command and get the actual value and compare it against the expected value that the accelerometer sends back. So let's go ahead and F10 over that. And we see that the transferred bytes is -1. And what that means is that nobody acknowledged that address. That, again, we saw that before. That was that on address 0x6a. There's nothing on our I2C bus that when it saw that address being written to said acknowledge. And so because of that, we didn't write out the command and we didn't read back a command. We just had the address and nobody acknowledged it. So we're basically at this point going to exit with a failure, and we're exiting, close our peripherals and say exit. So no such device or address. Nobody's listening on 6A. Okay, so cool. We kind of expected that since our Arduino is hooked up, but there's no code running on it to do anything. So now the next step is to go ahead and program our Arduino to actually talk I2C. So one thing you could do, I'm going to move this over here so that you can see my full thing and the webcam doesn't cover it up, is if you go to examples, and I haven't installed any libraries at all. This is just the Arduino IDE from Arduino.cc that I've downloaded. I can make a video about how to install that IDE and walk through some of that as well. But under the Nano, there's this Wire library, which Wire is basically a subset of the I2C protocol. And so there's a slave receiver and a slave sender sample. And those are really good. So this is the slave receiver sample. And then this is the slave sender sample. And so we're basically going to be using a combination of both of these to make our device that's going to be able to have our Arduino both send and receive data. And so basically, it's using that wire library, this wire.h that we're going to want. And then it listens, it does a begin on the address. And then if you're a receiver, you're going to have this onReceive that has the name of a method. And this method is right here. And it takes an integer of how many bytes to receive. And then you can do this Wire.read to get those bytes. And then it also, on the other side, it's also listening on address 8. And on request, you pass in this other method, requestEvent, and then in requestEvent, you can see you can use Wire.write to write out messages. So receiveEvent is where we read our messages, and requestEvent is where we write our messages on the bus. Cool. So hopefully that makes sense. These are great sketches you can come back to refer to if you need them. I'm going to go ahead and just close them out and put our code side by side. So, all right. So this is just an empty sketch. So what's the first thing we need to do? That's right. We need to include our library, which is wire.h. Yep, you got it. Cool. So let's go ahead and Control S to save that. And let's click on the upload button. So we're uploading it into our Arduino now, and it finished. It's done uploading. So Arduino is now ready to rock and roll. Cool. So let's go ahead and run that sample again. And again, my sphere is connected to the Arduino on the headers that we saw earlier that were specified. Okay. And we're there. I'm going to hit continue. Okay, we're about to open, continue. And we see that no such device or address is still the error we get. Which makes sense because all we've done is include the library. We haven't used it at all. So totally makes sense there. So in our setup, what we saw was that there's a wire.begin, and you pass in the address. And in their case, they had an address of 8. So let's go ahead and save that and upload that. So I'm using 8 because that's what was in the original sketch. But this is the address that our Arduino's going to acknowledge data and send data on. So address 8. So we've uploaded that. So let's go ahead and run our sample again. Okay. And this time I'm going to step into that who am I. So we're going to go ahead and say continue here. And then here I'm going to kind of F10 through these real quick. So we're opening, we're setting our bus speed, 100 milliseconds of timeout. Our target address, again, remember, this is not 8. This is address 6A that it's going to send stuff to on POSIX commands. Read who am I going to F11 into that. Go ahead and set a breakpoint here because we're going to, in the future, want to just jump into this code because all the other code was working regardless without any errors. Okay, so now we're going to send out on address 6A. We're going to say, hey, address 6A. That's the address lines. We're going to hopefully get an ACK, which there's no reason we should because we're listening on address 8. And then once we get the ACK, we would send out this instruction 1F for 1 byte and then read back the actual value. F10. And sure enough, we got -1. Nobody acknowledged that address 6A. And let's just go ahead and run. And we're exiting no such device or address. Cool. So hopefully that makes sense. So now this is where the fun begins. All right. So 0x6a. So let's go ahead and save that and upload that. So now we're actually going to listen on the address that they're using. So it's done uploading. So let's go ahead and run it again. Alrighty. And we're running. Okay, continue. Okay, I'm going to clear this breakpoint. Continue. Okay, so now we're going to do that write and then read again. So F10. Look at that, we got 2 bytes. So 1 byte we transferred was this byte of saying, please, whoever's on this address, tell me that. And the reason we transferred it was because somebody, basically this address here, is now on the bus that acknowledged it. So when it saw that address, we sent back an ACK instead of the NAC. So negative acknowledgement didn't happen. We did a positive acknowledgement, pulled that wire low. And then we read back a value, which it read it as a 0. So the actual value is 0. So good news. We're going to get farther than we've ever been before. We actually got there and we did an exit because we read back a value of 0. Unfortunately, at this point, our actual is 0. Our expected is 105 or hex 69. They're not the same, so now we're going to exit with unexpected who am I value. Okay, cool. So that was pretty exciting. So next up, I think what's useful is to let's go ahead and let's do that on receive and on request type of stuff from the sample we saw. So we're going to go ahead and in our setup, we're going to say wire on receive and then our method. And then we need to go ahead and make that method. And remember it took how many? And I think what would be useful at this point so that we can see what's happening would be to actually use the serial library so that we can use the serial monitor that's in this thing. So let's go ahead and do a serial begin. And you can pick whatever speed you want. Most of the samples use 9600. It's kind of slow, so I typically go a little bit faster for the speed for the serial port. And if you want, in examples under communication, there's examples of basically how to open that, wait for the serial port to connect, needed for native USB port only, and then an example of writing out a message. So we'll go ahead and do that too. Not everybody does this step, but let's go ahead and do that. Okay. And then serial.println, and that prints out a message to the serial port. So let's go ahead and here we'll put that serial.println, receive event, And then actually let's do print so we're on the same line. So println goes to the next line after it's done. And we'll do a println on this line. And we'll say how many. Cool. Okay. So I could do another talk on serial as well if we want to go into that in the serial monitor. But basically all we've done is we've now added the ability to go into tools and have a serial monitor to see the data that we print out so that we can kind of see what's going on our Arduino. And then we added this on receive so that whenever message gets received for address 6A, it'll call this receive event. Cool. And in our receive event, when we get a message, we're going to print out to the serial port receive event, and then however many is in that, how many. So let's go ahead and upload that. Hopefully that makes sense. Cool. So we're going to go to tools. It's done uploading in serial monitor. And then down here, make sure that you've picked the same baud rate, either 9600 or 115.2 that you specified, right? Because you're going to want those to match. So let's go ahead and start debugging. Cool. And continue. All right, we're at our write then read. This was the one that succeeded last time. So let's go ahead and F10 that. And we see that we have a receive event of 1 byte. So our receive event got called and it printed out receive event, and then the how many was a 1. So receive event 1 byte. And that byte is actually this command, who am I reg ID. This 0f is the byte that was sent. Cool. So we got the receive event and we had 1 byte. Our transfer bytes was 2. And our actual who am I that it got back was still 0. So the rest of this is basically the same. So unexpected who am I value. Cool. So now what we need to do is we basically need to read that byte to know what's going on. But before we do that, I actually want to do the on request as well. So let's do that so we can see what's really happening here. Wire on request event void request event, and that doesn't take any parameters. And we're going to do a serial.println, in this case, request event. Okay, so we saw that receive event happened. We saw that we were passed a value of 1 byte, and we printed that out. And then now we've added that if request happens, we'll call requestEvent and print out requestEvent. Cool. So let's go save that and upload. Okay, so that's uploading. Just finished. And let's go look at the serial monitor. So serial monitor, and sometimes you have to clear this clear output button. Click that. Cool. So we're here. We're going to F10 over it. And what we see was receive event got called with 1 byte, which was that who am I command was 0f. And then request event got called, and that actually got called because we did a read. So this read was trying to read data from our Arduino, and so it called request event to do that. And we know that these two values are different. I just want to go ahead and jump over this code for a minute to show you a little bit more code. So we can do Control-Shift-F10 to set the focus to this next line down here and skip over this exit path for a minute. So now these are just different ways to also do, so we did write then read. This is doing the same thing, but it's just the write first. So it's going to do a write on that address with 1 byte of 0x0f. So let's go ahead and do that. And it says it transferred 1 byte. One thing we notice up here is that nothing changed. And so what that means is we didn't get another receive event. And we'll look at that in a minute. And then we're doing a read. And so we did a read at that address to get the actual value. And we saw that we got an actual request event that happened again. And then I'm going to skip over. Again, we know that the actual and expected are not the same. So let's go ahead and set next statement to there, or Control-Shift-F10 if you want. So we're doing a write. Again, we don't see that receive event 1 that we would have expected, but we did transfer 1 byte, so it did acknowledge that reg ID. And then we're going to do a read. And again, we see that we got another request event where it's trying to read what the value is. And you notice that this is using the POSIX API. And so it's doing that default address we set up in our initialize. Cool. All right. So we still have not written out the right value of who am I. It keeps reading as 0. And we also see that receive event gets stuck. And that's because we haven't read the event that we received. So that's why that's happening. So maybe next up we'll do the read. Let's do that. So int data equals, and we could say byte, it doesn't matter. Wire.read. And then let's go ahead and we'll print out receive event data, and then we'll print out the data. Okay. So upload that and run again. And so now we're actually consuming that. When they sent us a byte to read, we actually are going to read that byte. Cool. So here we are. Let's open up our serial monitor. Okay. So let's F10. Cool. So receive event 1 byte, and the receive event data is 15 in decimal, which is the same as this value here. So cool. We actually read the instruction, the byte. We were able to read that 1 byte, and we saw it was 15. And then we got a request event, which we didn't do anything with yet. We transferred the 2 bytes. Our actual value is still 0 here. So again, that's going to fail. So I'm going to set our next line, jump down here. And now we're going to do that write again, which last time, remember, when we did a write, we didn't receive the event. But now we're going to do a F10. And you can see this time we got another receive event of 1 byte. And this time the data was also 15. So that's what was sent out. Great. And then we're going to call read. which is requestEvent on our side. Cool. Again, these are not the expected values, so we're going to skip over that. Control Shift F10, set our next line. Use the POSIX, doing a write. Cool, we saw receive event 1 byte with the data of 15. Awesome. Awesome. And then read did a request event. And again, the actual data just keeps moving back 0. Perfect. All right. Cool. So that's exciting. We now receive each time it's sending us a byte. We see that. And we saw that if we don't read as many bytes as it told us, it will get stuck and we won't be able to get any more receive events until we've done the reading that we need to do. Great. So what's next? Next, let's go ahead and actually reply back with the data that we wanted to. So we will do a Wire.write of the expected value, 69 that they're looking for in hex. So let's save that and upload. Okay, so what's going to happen is probably not what you think is going to happen, but I think this is a good lesson to learn. I spent enough of my life learning this that hopefully it'll just take you less than 30 seconds to learn this lesson. So we're going to do a write then read. Let's go to our serial monitor. Cool. F10. Transferred bytes is 2. We got that receive event of 1 byte with data 15. And then we wrote Wire.write 69 as the answer. And then we got a request event. So what is the actual who am I? It's still 0. And so you're like, but wait, we wrote out 69 in hex, but what we read was we got a 0 back. And that's going to be true for all these, so I'm not going to show you, but if you set your next line down here and did the same thing, you'd see that happen again. And so that might leave us scratching our head for a while trying to figure out, well, how am I supposed to write out the right value? The answer is you're not supposed to write out the values during the receive event. You're supposed to, when you're receiving, that's where there's an address line of 0x6a, and it's sent out. We said acknowledge, the Arduino said acknowledge, and then it sent out a certain number of bytes saying, I want to do a write, and it wrote out that many bytes, which we were able to read. Then what happens, we saw, was then it sent out the same address, 066A, and it said, I want to do a read of a byte. And so there was this request event that we saw, and we printed out request event. And that's, during request event, that's your time to write back answers to those requests. So let's go ahead and delete this code. And let's put it where it belongs. Cool. So receive is when you read, and request is when you write, because the master is requesting data, so you write back the data it's requesting. And receive is when the master is telling you data and it's your turn to receive it. Hopefully that makes sense. All right, this is the exciting moment of truth. Or at least we hope so. Okay, F10. The actual who am I is now 105, which is the hex 69. And so, yay, we were able to send that back. Oh, I didn't do the serial monitor. Sorry about that. Okay. And so they matched. So we get to keep going. We're doing a write. So receive a byte with 15 in it. And then we're sending a read, and we replied back with a value of 105. Great. And those map to the right values. And we're doing a write. Okay. I'm not sure what happened there. I actually kind of expected to see... Oh, because I cleared the screen, so we did see that. I just missed it on the screen. Cool. So now we're doing a read. And again, the values are correct. And so we've successfully implemented the method of read who am I, talking to our Arduino on address 6A and getting back the expected result. So awesome. So next is reset and set sample range. So let's go ahead and step into that. Okay, so it's going to do a write. In the reset command is the structure here, and the size of reset command is 2 bytes. So we're going to actually see 2 bytes get called. Cool, so we got receive event of 2 bytes of data. The first byte we read was 18, which is that first byte here. The second byte was 01, which we have not read. And as you recall, if we don't read everything, for now on, we won't get any more receive events until we've read both bytes. So now it's going to do a write and then a read. Again, we won't even get the receive event here. And so it transferred 2 bytes. And all we saw was the request. We didn't see the other one there. And the size it actually passed was a size of 1, where it keeps now reading 1. And we still replied back on the request event with our value of 69. And this loop keeps checking to make sure that that lower, there's a not here, so that lower bit needs to not be set. And it is, so we're going to just get stuck in this loop. Okay, so let's go ahead and stop. Cool, so hopefully that makes sense what's going on. And so what we can do here is you can either do a while calling wire.available, or you know how many bytes because it was passed in. And so you could loop that many. So let's just go ahead and loop that many. Int I equals 0. I is less than how many? I plus plus. Okay. Cool. Save. So this is going to just loop however many times and going to read that byte and print it, and read the next byte and print it. So that hopefully fixes why we weren't seeing any more receive events show up. Okay. Now who am I actually? We can clear this breakpoint because this is all working now. So F10 up. Let's do this serial monitor. Sorry. There's our write with our event 1 byte. There's our read. We wrote out the expected answer. They matched. There's our write 1 byte. Here's our read. We wrote out the expected answer. They matched. Okay. F11 into this. And let's go ahead and set our breakpoint here. So this time we wrote out 2 bytes, which is this byte and then this byte, and we can see that we saw the size was 2 bytes, and now our loop read 18 the first time and then 1 the second time. So our loop ran twice. How many was 2? So it went once, twice, and then it exited. Cool. And great. And then now it's doing a write of 1 byte and then reading our answer. Okay. So let's see that happen. So you can see we got a write of 1 byte with 18. Unfortunately, our answer is still 105, and 105 has that high bit set. So it'll just keep in a loop passing us 118, 118, 118, waiting for us to finally write an even number back. But we keep writing 69, which is an odd number. Okay, so cool. So let's go ahead and stop debugging. So now I guess what we need to do is not always write 69, but we need to write 69 if the answer was who are you? But if the question is 12 and it's a 1 byte, we're going to want to write an even number, probably like 4 if you actually look at the data sheet. But cool. So let's figure out how do we want to do that. Maybe the next thing to do is to throw away this code, and we'll start doing like some logic with if-thens kind of thing. So let's try that. So I'm going to throw away the loop. But remember, it's critical that we read the right number of times, however how many is. But let's go ahead and we'll just do that. So we've read it. If the data is, if we're in the who am I case, which is 0f, then we want our response to be 69. Okay, so let's go ahead and make a variable called response. We'll make that a byte. And let's move it up to the top. And let's initialize it to 0 just for starting. Okay, so if we have that, we're going to say the response is 69. Otherwise, if the data was this 0x12, and the how many is 2, then this will do a println of, that's the command it was doing to reset the device. Okay, so we'll print that out. And then we'll also do a, let's do data equals wire.read to read that second byte. And we'll do println. Hopefully this makes sense to you. So we read that second byte, and then we printed out a message that they did a request to reset our device. And we'll print out this one command. Okay. Otherwise, if the how many was 1, then that's what we had here, where they wrote out to our address just 1 byte with this 12 code. So then let's go ahead and say println come out of reset. We are out of reset. And so now this time we want to change our response, and we'll just go ahead and set it to say 4. Okay. And then otherwise, we will, let's just go ahead and do a while loop that says while wire.available, we will do data equals wire.read, and then do serial.print data serial.println the data. So if this doesn't match one of these cases, we definitely want to read out all the data so that we continue to get called in the future. So that's kind of a big chunk of code, but hopefully not too hard to follow. Also here, we did have the how many should be 1, just in case there's, for some reason, it sends us out with multiple. Let's do that. So let's go ahead and upload that. And then here, instead of sending out this code, we want to send out response. Okay. Does that make sense? So it'll call us with how many. We set our response to 69. Let's go ahead and serial println okay, so we'll do that to show that we set the response. And then here we set a response as well. And then these are the ones we don't do anything. Okay, cool. So let's go ahead and upload. Great. It's uploading. Okay, I've got the serial monitor up. So we saw this was the received event for who am I 15. We set our response to 105, and then in our request event we replied back with that value, and then we got another one, who am I, we set it to 105, and our request event we replied back with the value, and then another one, who am I, and we replied back with the value. Cool. So now we're here. F10, we can see that we did a write of 2 bytes, and the first byte was that 18, and the second byte was a value of 1, which is from here. Okay. Now we're doing a write of 1 byte, and then we're going to read the value. And so we got a request of 1 byte with that 18. So we're going to return back a 4 next time that we're asked. And then we got that request, so we returned back a 4. And so now we exited the loop because this checked that the value and the lowest bit is blank, and then we inverted that with the not. So cool. Now let's look here. Great. We are writing out 10, which is 16, and then a second byte, which is this 18 hex or 24. And you can see that we didn't have a handler for this 16 or 10 hex. So we fell in here and we printed out this extra data of 24. And the command, this was a write. Cool. And so that command is used to set the range and the frequency. Cool, so perfect. And we're good there. So let's go ahead and look at, I think that looking at the data sheet and understanding some of this is maybe our next step. Before I handle 10 and then just hard code 18. But let's go ahead over here and we'll say else if data equals hex code 10 and how many equals 2. We'll print out set range and frequency. And then we're going to go ahead and do that. The data equals Wire.read to get the second byte. And then instead of printing it, we want to basically understand what these values mean. So let's go ahead and scroll up to the top. And there is this is the data sheet we actually need, is this LSM data sheet. That'll explain what all these different pins are. Let's hope that I can find a data sheet. Here's one. Okay. So 10, what we're trying to understand was that they sent us an instruction where this first byte was 0x10. And the second byte was 0x18. So 0x10 is 10 hex. So the actual instruction is CTRL1XL. Cool. And then there's this bit mask of different flags. These ones, and these ones. So you can see that the accelerometer scale, the 2 bits, if they're both set to 0, it's 2G. If it's 0, 1, it's 16. If it's 1, 0, it's 4. If it's 1, 1, it's 8. And these bits, this FS piece, are these 2 bits. So that's 0. So this is like a value, the first bit. So this is, if this was set, this would be a 1. If this was set, it'd be a 2. If this is set, this would be a 4. If this was set, this would be an 8. And so, again, we know that we're trying to set to get 4G. This would be set 8. And then this is set to a 0. So this value should just be 8. So let's go ahead and try that. If data, we're going to shift by 2. And then we'll mask off. We only want these 2 bits. So we'll mask off by 3. I could do some later if you want me to walk through logical anding and oring and stuff. We can look at that. And we basically expect this to be a 2, right? Binary. So serial println, speed is plus or minus 4G, else unsupported, I guess. So we'll assume that it's got to be this value we're looking for. And the next thing that they sent us, in the sample, was 12.5 hertz. So that's these 4 bits. So then we're going to say if data shift 1, 2, 3, 4. And if that is a 1, then we'll println 12.5 hertz. Else serial println unsupported frequency. Okay. So now when we read this instruction, we'll read the second byte, and then we know that this is a set range and frequency. If the second byte if that bits are set, we'll print out this message, and if those bits are set, I'll print out this message. It might make sense to also print out data, so let's just do that so that we can troubleshoot if things go terribly wrong. Okay, cool. So hopefully that's making sense. Okay. Start debugging again. Oh, throw up our serial monitor. Clear the output. And go ahead and run to the breakpoint. So that's the who am I's. Now we're in here. F10. So we got that instruction. So that instruction was hex 12 and then a value of 1. So let's go ahead and look back here at hex 12. That's this one, control system, and a value of 1. So software reset. And software reset, the default is 0. And if you're set to 1, you're supposed to reset the device. And then we're supposed to clear it when we're all done. And looking at this, you'll see that the default values are 0, 0, 0, 0, 1 for this bit, 0, 0. So that's why 1, 2, 4, that's why I chose 4, was just to kind of better simulate this device with the default values you'd expect. Cool. So we're there. So we're waiting for the device to come out of reset. Okay, we're returning out of reset. We returned that value of 4. Exit that loop. Now we're going to send this 10 with a value, a second data byte of 18. And this one we can see it's set frequency and range. Data was 24. Unsupported speeds, it looks like I messed up that part of it. And then this part actually worked at 12.5 hertz. Cool. So 24 is right. So I'm not exactly sure what I've got wrong on this thing. So let's go ahead and figure that out real quick, I guess. Back on register 10. So we're trying to get these 2 bits when we shifted it, and then we ANDed it. So let's go ahead and just, to debug that, we'll make a new variable called speed. The speed, and it will equal data shifted to and 3. And then we'll do a serial.print the speed, println the speed, okay. Oh, and we only want one and because we're doing Boolean logic here. We're trying to do bit logic, sorry, is what we need to do. So that's what a single and. So let's go ahead and see that. Sorry about that. But I think it shows you kind of how you debug as well, which is always good, hopefully, to learn. So let's go ahead and serial monitor that. Okay, we're going to start debugging. We're getting pretty close now. Okay. Out of reset. Okay, here's the moment of truth on this one. Cool, the speed is 2, and 2 prints out this message. The speed is plus or minus 4G, and then 12.5 hertz. Cool, and then return success. And let's continue to route. And so now what you can see, and something we kind of glossed over before, is we keep getting a byte sent out with the request of 30. So going back up into our init, there was a periodic timer that was set for once a second. So every 1 second and no nanoseconds, call this event handler. And so that event handler is getting called, and we consume that, and then we are setting our status reg here. So let's go ahead and set our breakpoint. Okay, so now we're in that handler. So we're going to write and then read. So we write 1 byte of 1E. Great. which is 30 decimal. And then they read back the status, which is a 4 here, and the transfer bytes is 2. And then they check to see if this value is set or not. The status has a 1 or not. And in our case, again, the data that they got back was just the 4 that was left in there from last time. So that's not true. And so we print out a message of no accelerometer data. So we really want, when someone sends us this 1E, we want to say that we're ready. So let's go look at 1E real quick. Over here and see what that's all about. 1E is the status register. So the bottom bit, this bit, is whether or not accelerometer data is available. By default, you return no, but if it's a 1, then it's saying it's available. And then this is the gyro and the temperature. So we need to return a 1 after a request for our status. So let's go ahead and do that. Okay, we can stop this. Okay, so else if the data is 1E and how many is 1, println and we want to set, in this case, we want to set our response to 1. All right, so we're going to go ahead and say okay. Let's go ahead and upload that. So when we get this 1E command, we're going to say, yeah, we have accelerometer data. So we're going to run this again. And I'm going to keep the breakpoint on this timer so we can just run until we hit the timer this time. Okay. Cool. All right, we're in our timer. Write then read. And oh, I didn't show our serial monitor. Sorry about that. But we can just hit continue and we'll get another timer in a second. Okay, so we're doing the write and read again. Cool, so this time we got that instruction. And that's that status read. So we're saying we have accelerometer data. The read request, we replied back with a status of 1. Great. And so now they're actually going to try to read that the z-axis, 2 bytes. And so for that, we're going to pass in a request for this one, which is peak definition 2C, and then they're going to read back our response, and the transfer bytes is 3. And then let's go ahead and, so in this case, the reason it's 3 is because what they've read back our response in was this 16-bit thing instead of an 8-bit thing. So this size of is 2. So it's 2 plus 1 is 3. And now we've read back our Z raw is -255 right now. And it's going to print this out. Cool. And it prints out some acceleration. So what we want to do, let's go ahead and set a breakpoint here. And we'll run it to continue. Okay, so it's asking us again, do we have accelerometer data? And we're going to say, yes, we have accelerometer data. The status matches, so we have it. And again, it's going to do this write for 0x2c, and then it's going to read 2 bytes. So 0x2c is the next thing we need to do. Okay. Else if so again, it's a 1-byte request that says that. And let's look up 2C real quick, just to understand what that instruction is. 2C is a 16-bit word in 2's complement. And so that means we're supposed to reply back with 16 bits, and it's the z-axis. Cool. Println and so now the challenge is our response that we have is currently only 1 byte instead of 2. So, but let's go ahead and reply back with, I don't know, well, let's reply back with a decimal number. That way we can see it. So when we get this request, we'll reply back with a decimal. So we're only going to write back 1 byte instead of writing back both bytes. So we'll need to figure out a way to return 2 bytes instead of just 1. Okay. Cool. Pull up the serial monitor. Go ahead and run that. And run again. Okay, we can clear that. F10. And so this time our raw data is that we've read back is -214. Cool. So let's go ahead and let's change our code to actually return 2 bytes in this case. Okay. So Next up, we need a way to return 2 bytes instead of 1, or maybe an array of bytes and some data. So let's do, let's look, I was gonna do like change this to a byte array of say 2 bytes. And length is say 1. Let's see if this is correct syntax. No, so this is saying here we need to put this in response 0 and length is 1. Responsive 0, length is 1, and responsive 0, length is 1. Responsive 0, length is 1. Let's see how that works. Okay, and then this println, it's also response of 0. We should probably refactor these to a method, a helper method. Cool. And so Wire.write, we could either loop at this point, or I believe that Wire.write has a another syntax where you can pass the data and the length. And the data is an array of bytes, and the length is the number of bytes. So let's see if we can get away with that. So data and a length. Cool. And then finally what we're going to want to do is here, we're going to want to set response of this to a 0 and say the length is 2 for this one. Okay, so let's go ahead and upload that. No idea how many mistakes I just made, but let's run it, see what happens. Okay. So this first time we're just going to blow through it. So the 105s, the who am I's, we've passed all those. Good news. The reading our samples, we passed all those and passed out the right data. So good news. The status, we replied to that. Good news. And now for this one, they did the write then read, and our raw is now 42. Awesome. So great news. And then they're going to do some math to figure out what the accelerometer reading is there. So let's go ahead and bring up a calculator real quick. So if we wanted a number that's 0.122, and then they're dividing it by 1,000. So it's about a value of 8,000 to get a value of 1 for our accelerometer. Cool. So let's go ahead and say int random of about 1,000. And then this is the high value. So we'll shift that there. And then this is the low value. Okay. I just lost a key on my keyboard. Good times. Okay, so let's go ahead and okay, we'll upload that. Okay, we're done uploading, so let's run it. Which button are we missing? It's hard to see, but we'll come back to that after. All right, let's run it again. We're running at F10. And so we did the write then read for the z-axis, and we're returning a value of 8807. Okay. And sure enough, our g value is just about 1. Okay, I'm going to clear this breakpoint. We'll run again. And now we're returning a different random value, you can see. So we were returning a random value between 8,000 and just under 9,000. And so we keep returning these random numbers between 8,000 and 9,000. And over here, you can see now we're returning an acceleration around 1g. So there you go. We've managed to simulate a device in our Arduino, look through each one of these things, respond to all of them, understand the different spec for being able to do that stuff. You'd probably want to do some code cleanup next, some refactoring, pulling out some of these constants up above, probably put pound defines for your, instead of hard coding 6a, you'd probably come in here, do that kind of stuff. Let's go ahead and upload that to make sure it's still good. You can see while we're uploading, things failed. And now let's go ahead and run it again. Make sure that this pound define didn't break anything. I recommend always taking small steps. That way, if you introduce a bug, it's not too far away from where you just were. Saves you a lot of time troubleshooting. Cool. And everything's still working. It's still replying, and the data's still happening here. So Hopefully you found this helpful. You can walk through this and understand all these, correlate them back to the data sheet, and understand why we sent the responses we sent. And in this case, yeah, that's all I really wanted to show you. One other thing that's kind of fun is to talk about the timeout. So let's do that real quick. Just when you thought you were done, right? So here's some code that is basically takes about 3 seconds to run on a Arduino Nano. And we do the print T because otherwise it could get optimized out. So this will take about 3 seconds of looping to calculate some value. Okay. And save this and upload this. So when we get a request now, a request event, it'll take 3 seconds and then we'll print out T and then we'll say sending response and we'll send that response. Great. So let's go ahead and clear our output and kick off our debugger again. And this I'm going to do a step into because 3 seconds is a really long time. So let's go ahead and see what happens here. F10, F11, step into. Okay, we're just going to step over this stuff. We're setting this up, opening up our port, setting our bus speed to 100 kilohertz, setting our timeout to 100 milliseconds, but our code takes about 3 seconds. Setting our default address for those POSIX calls, and then I'm going to go into read them. Who am I? And this is where it gets interesting. So you can see that we got back -1, and so it failed to do that call, and it's actually kind of interesting that you get back a -1 on timeouts, because it did transfer. I mean, it transferred this 1 byte of 0f onto the bus, and we set a response, but we took too long, and so it timed out. And the actual who am I does not match to the expected. And let's go ahead and actually set this to something else, just so we can see this as well. I think this is important to understand. I wish I had set a breakpoint on line 176. So we could go a little faster. Cool. I did set a breakpoint. So we're going to go ahead and continue. Okay, so we're here. Our current actual is set to a 1. So F10. Our transfer bytes is -1. So we got that it timed out. So it says nothing got transferred. We saw it actually did transfer 1 byte, which was the 0x0f, that 15. We set our response, but then our response took too long to reply. And our actual is still the old value of what it used to be in there, which is a 1 in this case. So I just kind of show that it's not getting set by our code, it's just getting set to a 1. And the transfer bytes is -1, even though 1 byte was transferred. Okay. Some interesting things also is while you're in requestEvent, you can't do stuff like If you try to use like a delay, the delay doesn't actually do anything. Millis, if you call it multiple times, gets the same value each time and stuff. So some of the clock stuff when you're inside of this event is disabled. But basically, we saw that it took about 3 seconds. So, and we saw that this failed. Okay, great. So you probably can predict what I'm about to do, maybe, which is to change our timeout. So we're going to give ourselves 6 seconds for our timeout. And we're going to go ahead and run it with a 6-second timeout now instead of 100 milliseconds. Okay, so now we're going to do that call that was failing last time, F10. There you go. And you can see that we managed to actually wait the 3 seconds needed. And so we transferred 2 bytes. And the actual who am I, instead of being a 1, is the 105 that we're expecting, the same as expected. And so now we can continue. Okay, we're now in here. So it's painfully slow because each time we're spinning around for 3 seconds doing this loop calculation. But sure enough, we are getting through it, sending data, and our accelerometer still works. And so what that shows you is if your request event takes any time to do stuff, you may have to change that that timeout. So hopefully that answers that. What's that 100 milliseconds used for, and how, pick a reasonable number for where you want it to work. And then the warning that when transferred bytes is -1, that just indicates an error. It doesn't actually indicate how many bytes were transferred. So, hey, it's been lots of fun. And I'll make another series about kind of how to physically hook stuff up and maybe some of the setup on one side or the other. But hopefully you found this useful. And go ahead and reach out to me with any questions or comments. Thanks a lot. Bye.